Okay, so my name is Daniel. I'm an astrophysicist and I like to get high.
I saw it.
See, and some people here too, right? But maybe not what you were thinking. I was, of course, talking about getting high on mountains, for example.
Me too.
When you're an astronomer, you have to go to really extreme, ugly places like Hawaii or Chile to do your job. We would have a couple of times. So you have to go to Hawaii and Chile to observe, so really high up on mountains. This is what I mean with getting high, of course. Or if you want to get really high, you build telescopes in space, like Cheops, which you already heard about, built here in Bern, or the James Webb Space Telescope, which is basically the next Hubble. And since I'm pretty vain and also quite a good scale, I took pictures of me with Cheops. So you see, as Esther already mentioned, a really tiny 30-meter mirror. And then in comparison to this 6.5-meter diameter, the Hubble Space Telescope, gold-coated beryllium, so for the connoisseurs from you. And these two guys are really going to help us to do the research that I'm going to do. So getting high, you go up on mountains or up in space. So the question then is, why getting high, right? So one would guess, yeah, you know, if you go up on a mountain, if you go up in space, you're kind of closer to the stars. But that doesn't really help. If something is like a bazillion light years away, getting a kilometer closer doesn't help at all. The actual reason is what you see in the image, the atmosphere of the Earth. It's a little bit when, you know, when Swiss people like to get high, what do they do?
Zwiebeln festival.
Go up in the mountains. If you go to the mountains, you know, the first, 90% of the way you take a train is pretty straight, and the last 10 kilometers you go, up the hill with a funicular or something, and then the last 100 meters up to the peak are really the hardest. And it's similar for light that comes to Earth. It goes for millions of years, thousands of years, just straight through vacuum, and then just on the last few kilometers it hits our atmosphere. And then it gets, bumpy and steep, and some nasty things happen to all the light that arrives. So this is the reason why we get high, to basically collect that light before it falls through the atmosphere. And it's even worse for a certain kind of light. You all know this, for example, from UV radiation, that it doesn't pass through the oxygen, the ozone layer. So that's why we only get like slightly pink and not completely burned if you go into the sun. But that also means if you're a UV astronomer, want to collect UV light from the stars, you have to get above the ozone layer. And different kinds of light, different parts of the electromagnetic spectrum, how we call it, go to different depths into our atmosphere. And it's no surprise that most of our telescopes are optical telescopes on the ground, or radio telescopes on the ground, and that our eyes are adapted to the optical spectrum, and that our phones work in the radio spectrum, because this is the only kind of radiation that actually passes through air, passes through our atmosphere. If you want to do, as I mentioned, X-ray astronomy, you have to go to space. If you do UV astronomy, you have to go to space. And even for the infrared, so the light kind of next to us, you have to get at least up to 10, 15, 20 kilometers. And you can see a plane there, right? So you say, yeah, that's maybe just to say, what the altitudes are that planes go to. But actually, there is a telescope on the plane called Sophia. Sophia stands for Stratospheric Observatory for Infrared Astronomy. And that actually works, the acronym also works in German, is the Stratosphärenobservatorium für Infrarotastronomie. It's built 80% by NASA and 20% by Germans.
Yeah,
and it works.
Honest.
And then you can see it's basically a pimped Boeing 747. And when I was a little student, just started my undergrad studies, parts of Sophia were built at Cologne University where I was studying, and my biggest dream was to maybe build an instrument, put one screw on an instrument that one day is going to fly on Sophia. So really one of the things that motivated for my career. And today, 15, 20 years later, I'm standing here and can actually report that I flew myself on Sophia. Here you see flying over the glaciers of Mars. Paying attention, that was the Grand Canyon. Actually, this is how it looks like inside when you're working, and Sophia. So actually, there's if you want to get high, not medium high between mountains and space, there's Sophia telescope on the plane. And again, me to scale, just let you know that Sophia is roughly the size of a plane. Okay, so you got there. So what about the aliens? So when I talk about aliens, I'm talking about exoplanets, so-called extrasolar planets, planets around other stars than our sun. And just this morning I looked up the number right now. We are at the count of 3,725 of these alien worlds that we found around other stars. And that's actually pretty hard. It sounds easy, 3,000, but it's actually pretty hard. And this is kind of shows you the challenge that we have if you want to observe exoplanets. So this is real data taken from a solar telescope, and this tiny black dot that you may or may not see passing through the image here, that's the planet Mercury moving in front of the sun, between us and the sun. And that gives you an idea. We are looking for these tiny black little dots next to these giant glowing balls. So this is our challenge if we want to find and analyze these exoplanets. But this video doesn't only show the challenge, that also shows you the opportunity, one of the methods that we use to observe these planets. And I think Esther mentioned it already when she introduced TESS and Cheops. We can also observe these transits. When we are really lucky, we can observe these transits for other stars. So a planet is moving between us and their host star and doing something similar that Mercury is doing here with the sun. And then we get these dips in brightness. So over time, every orbit, the star gets a little bit dimmer, and again, really reoccurring period of the planet, like almost like a heartbeat. It gets these blimps again. And as you can also see, depending on the size of the planet, these dips are deeper. So you see, like a Jupiter-sized planet makes a much bigger dip in the light curve, in the brightness curve, than a tiny planet size of Earth or Neptune. So from these dips, we really know roughly the size of the planet, and then there are other methods that also give us. Oops, what did I do? Okay. So this is how we find these planets. But the same thing, we can even go farther and even get an idea about what atmosphere these planets are. So we can sniff the atmosphere with a similar method, because when the planet goes in front of the star, also some light of the star passes through the atmosphere, and some of the light gets absorbed. Some of the light gets transmitted depending on what molecules you have in the planet, and then if we take a spectrum, spread the light in its different colors, we get different signatures of absorption or emission from these exoplanets. And what we really just only see is this really upper, really thin layer of the atmosphere where the light falls through, and then depending if you have something in the atmosphere, if you don't have something in the atmosphere at that wavelength, your transits are slightly deeper or brighter. Deeper or a little bit fainter. And then we do something that we call a spectrum. So at each wavelength, at each color, we get a different depth of this absorption. And therefore we can say, okay, there's water in that planet, there's CO2 in that planet, there's methane in that planet. So this is the method how we actually get information about the atmosphere. So one of the coolest things that I find that we found out in this whole exoplanet theme is that roughly 5 to 10, some even say 20% of stars have planets that have the similar size and the similar temperature that Earth has. So kind of, we call them habitable planets. So next time when you get high, for example at Matterhorn or somewhere else, and observe the stars, just count to 10, count to 20, and then at least the 20 star, maybe the 10th, between the 10th and the 15th, 20 star, there might be a planet that has life. But what does that mean, Earth-like? I mean, it's just an invention. So if you hear Earth-like in the news, be skeptical. That's my message for you. Because if you look at all the planets that we know in our solar system, and I also call Pluto, I'm a nostalgic guy, so Pacific Beta 9, 339. So if you look at the planets and Pluto of our solar system. So technically Earth-like or habitable for us exoplanet guys and girls would be Mercury, Venus, Earth and Mars. So 4 of these would be Earth-like planets in our not really really concise definition. And you can see they are all different. There's not even two even similar planets. I mean, maybe the planetologists don't argue with me about that, but they are really, really different. So it only gives you an idea how many different planets might be out there and how unlikely it is that if we find an Earth-like planet, that it's really like Earth. And that's basically my take-home message here. So even if you find 3,000 of these planets, even if Elon Musk sends a bunch of electric cars to Mars and then follows up himself, this is the only planet we have. So to quote Carl Sagan, this is here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was lived out their lives. So no matter how many exoplanets we find, how Earth-like they are, this is the only planet we have, and it's also the only planet that has beer, so we better. Thank you.